This is video 522, and the goal of this video is to find exact values and verified identities using the sum and difference. So we're still looking at sum and difference formulas, but we're going to see a little bit more identities and continuing with finding exact values. So here we have a situation where they tell us something about alpha, angle alpha, that the sine is 4/5, and they tell us something about angle beta. Okay. Notice they also give us a quadrant that these angles fall in. And our questions are asking us for things like the cosine of alpha and the cosine of beta, which is something we learned in chapter 4 how to find. And then they're also asking for the cosine of alpha plus beta. Now, one thing that we're not going to do with any of these, since the question, technical difficulties there, sorry, hold on. So one thing that we're not going to do since it's asking for exact values, we are not going to find the angle. Because if we find the angle, it's not going to be an exact value. It's going to be a good estimate from our calculator. So we're not going to find alpha and beta. We're actually just going to use cosines of alphas and cosines of betas to find the missing information. So watch and learn, and you'll get a chance to practice this in class. So example 5, we know the sine of alpha is 4/5, and we also know that we can draw this picture in quadrant 2. Because in quadrant 2, those are angles bigger than pi over 2, but less than pi. And so I'm going to label the sides of my triangle because that's y and r, so I know it's 4 and 5. Now, in order to find cosine of alpha, I need to find x. So I'm going to start by doing that by just using a Pythagorean theorem. I'm not going to bore you with all those steps because I think that's something you can do on your own. And I get 3. So now I have 3 for that missing side, but it's not just 3, it's -3, and that's why it's important to draw the picture. You have to find the proper value, positive or negative. So -3 is your x value. So now I'm actually prepared to answer question A. The cosine of alpha is -3/5 because cosine is defined as x over radius, and my x was -3, my radius was 5. So I'm going to do something exactly the same for cosine of beta. I'm going to draw a picture in quadrant 3 this time because between pi and 3 pi over 2 is quadrant 3. And so my sketch is going to be down in the bottom quadrant, making my y value negative, and my radius is 5, and my y value is -2 over square root of 5 because sine is y over r. Now again I'm going to have to find x. Again, I'm going to use Pythagorean theorem. I'm going to carefully square this out though. I'm going to use parentheses and square the whole value, -2 square root of 5 squared. This one I am going to show a little bit more steps on. Of course, 25 is on the left, but what does this right-hand side give us? Well, -2 square root of 5 squared really means times it by itself. So in essence, I'm going to end up timesing the two -2's together to get 4. And then I times the two square root of 5's together. Square root of 5 times square root of 5 is actually just 5. Because remember, it ends up giving you the square root of 5 times 5, which is the square root of 25, which is just 5. And that's how I got the green 5 there. Now I'm going to go about and find that 4 times 5 is 20 and continue on my way. So I'm solving now for x squared, and I end up getting 5 is x squared, so x is square root of 5. So this one took a little bit more work, thoughtful, careful calculating. But I got an exact answer of square root of 5. Putting that in my picture, I know that it has to be negative because it's in quadrant 3. So make sure you add that negative on that value. Last but not least, I'll find the cosine of beta, which is just x over the radius, -square root of 5 over 5. And I'm done. I've got my first 2 answers for these first 2 questions. Now these first 2 answers were super important because they're actually going to help us with my next formulas. So if I'm finding the cosine of alpha plus beta, I'm going to use the formula for alpha plus beta, which is the following. I pulled from the formula sheet. Now I actually am going to plug in the values I know. These are not on my unit circle, but I have them all sitting right in front of me. I know that the cosine of alpha is -3 over 5 times the cosine of beta. Well, the cosine of beta is -square root of 5 over 5. Subtract the sine of alpha, which is 4/5, times the sine of beta, which is -square root of 2 square root of 5 over 5. Now I'm going to start multiplying this out. The denominator will be 25 because 5 times 5 is 25. And negative times negative is positive. 3 times square root of 5 is 3 square roots of 5. Doing it again. Negative, I'm subtracting, but because I'm subtracting and I'm going to get a negative answer, it's really going to end up addition. And then I multiply across the top and across the bottom. So again, those two negatives that I had here and here canceled out and made it a positive. Notice again I have the same denominators, so I can actually add these two together. And since these are also like terms, they're both square roots of 5, it's kind of like adding 3x plus 8x and getting 11x. So 3 square roots of 5 and 8 square root of 5 is 11 square roots of 5, all over 25. That's the solution for cosine of alpha plus beta, using the sum formula for cosine. Now let's repeat that process, but now we're going to do it for sine of alpha plus beta. So again, we're going to use a formula from our formula sheet. In this case, the sum for sine formula. Sine of alpha cosine beta, so 4/5 based on the original problem, times cosine beta, which is negative square root of 5 over 5, plus cosine alpha, which is negative 3/5, cosine beta, which is negative square root of 2 square roots of 5 over 5. Now simplifying again, I get a denominator of 25. On the top I get negative 4 square roots of 5 over 25, plus positive 6 square root of 5 over 25. Again, the top are like terms and the bottom are common denominators, so I can add across the top, and I'll get 2 square roots of 5 over 25. And that is my solution for question D. So you're literally plugging in what you know. You do have to find some additional values before you can do these formulas. But it's keeping everything exact. Decimals are not approved for these problems because we can find the exact values. Now let's look at verifying identities. So if we're verifying identities, we think back to some of the strategies that we talked about in class. So some of the hints that we talked about were making sure the values and the angles are the same. Notice on the right, it's cotangent alpha, cotangent beta, so they're single angles. But on the left, we have alpha minus beta. So my first step is to make it so it's just alphas and betas, no alpha minus beta. So I'm going to use my sum and difference formula, in this case cosine difference formula, which requires adding. And I'm going to replace the top with that formula. The bottom will stay the same. And I'm going to try and somewhat meet in the middle. So I'm actually going to replace the right-hand side with cosines and sines based on the definition of cotangent so that I can better see what I'm looking for. So I use the cotangent ratio identity. Now I'm going to start to look ahead and think about what I want. Well, I want two separate fractions because of the right-hand side is something plus 1. So I'm going to separate what's on the left-hand side so that I can slowly start to get something plus something. And notice when I separate it, I keep the denominators like. That's how we separate fractions. They both go over the denominator. The sine alpha and sine beta. They both went over the same denominator. Now I'm going to simplify. Notice on the right fraction, that just becomes a big old 1. Because something divided by itself is 1. And on the left, notice how similar it is to the other one. I'm actually completely done with my identity. Sorry, just skip past that. You're actually done because at this point you would just rewrite it like this, and then you would be done because you've gone in a full circle. Let's take a look at another identity. So again, we're going to start with using the fact that we are going to try and turn the left into the right. And we notice that this has just alpha, this has just theta, and the other one was theta plus pi, so we're going to use the formula, the sum formula for tangent. We haven't used this formula yet. So let's take a look. We're going to have tangent of theta plus tangent of pi all over 1 minus tangent theta, tangent pi. Now at this point I'm going to replace what I know because I actually do know tangent of pi. I can look on my unit circle and see that it's 0. So I'm actually near done here because on the top I'll get tangent theta plus 0, which is just tangent theta. And on the bottom I get 1 minus 0 because tangent theta times 0 will be 0. And simplifying that, it's just tangent theta over 1, which takes me back to where I started. And I've done my full circle and I've established the identity. So that's your final example for this video. So take a look at your checkpoints here. We're not going to do example 8. Your checkpoint problems are here. Try these, submit them on the form, and bring those questions into class. Thanks for watching.